Okay, we're going to end by looking at one more idea in our counting principles, and that is, well, this is old. If we have a symbol like this, it means the number of permutations of 6 objects taking 3 at a time. So say we have 6 people in a classroom, imagine that, and we're going to have a president, a vice president, and a treasurer. So we talked about something like that in one of our problems today, and we saw that you can calculate it like I do. I let this number tell me how many blanks or spots there are, and this number tells me where I start, and I go 6, 5, 4, and I get 120. Or I could use the formula, which will get me the same thing, and there's my work for that. So that's old news from today. So let's build on that. What if on this order matters? So up here, if we had, say this is president, vice president, treasurer. So we had Zach and Joel and Kate. Would that mean the same if I had Kate, Joel, and Zach? No, because each one has a different meaning. So the order does matter. But what if order doesn't matter? Well, we're going to cross that line right now. Let's talk about situations where order doesn't matter. Can you think of one where order doesn't matter? Let's go back to our classroom situation. Suppose we have 6 people and we want to make a committee of 3 from the 6 students. So we're going to have a committee to help make decisions on how long tests are and how much homework we should have. So we're going to elect a committee of 3 from the 6 students. All right, this time, if we put Zach, Joel, and Kate, isn't that the same committee as if I put Kate, Joel, and Zach? So we have the same 3 members in a different order, but it is the same committee. So in that situation, order doesn't matter. So we can't use our permutation ideas that we used up here. So what can we do? For this, let's see how we will do it. It's now called a combination. When order doesn't matter, we are going to use this symbol. Instead of a P for permutation, we're going to use a C for combination. I like to think of it as committee because it sort of carries the idea of behind order not mattering, but it really stands for a combination of 6 things taking 3 at a time. So when I talk about that, do you expect the number of committees or combinations of 6 objects taken 3 at a time where order doesn't matter, do you expect that to be more or less than the number of permutations of 6 objects taken 3 at a time where order does count? So let's talk about that by looking at an example. Let's say that I'm going to take 5 objects and I'm going to take 3 at a time. Now in the old school, before we crossed the line where order mattered, we did a permutation similar to that and we found that there were 60. So let's actually do 5 objects 3 at a time and see how many combinations we get. So I actually showed my work there. If you wanted to use the formula, they both come out to 60. All right, so let's do the letters A, B, C, D, and E, and those will represent the 5 objects, and we're going to take 3 at a time, and we're going to see if that comes out to more or less than 60. You have what you think it's going to be, so let's see if you're right. All right, so one, if I'm only going to have 3 blanks, so I can put in ABC. I can't put in CBA because when we're talking about combinations, CBA is the same committee, so to speak, or combination as ABC. So I have to have different letters on each line, or a different set of numbers. All right, I can have ABD. ABE, you can see I'm kind of going a pattern to, I'm following a pattern. ACD, ACE, A, D, E. I guess that's all the ones that start with A. So let me start with B. B, C, D. You know which one I picked next? B, C, E. There's no real order, but you can probably see a pattern I'm following. B, D, E. And now we'll start with C. C, D, E. And we have all of them. That's all the ones that are possible without repeating a set. So when you add those up, I got a total of 10. So 10 doing combinations, and up here we got 60 with the same numbers doing permutations. So you can see there's quite a bit fewer on combinations than similar problems that are permutations. So writing it like this, I notice that a way I can get 10 by mathematical formula or mathematical thought, I have 5 objects, 3 blanks, 3 at a time. I can fill in 5, 4, and 3. So far what you see on the screen is like a permutation, but we're going to have to reduce that by quite a bit. And to get to the right number, we end up dividing by 3 factorial. So let's see if that works. 5, 4, 3 divided by 3 times 2. 3's canceled, 2 goes into 4 twice, 5 times 2 is 10. So we did it by hand, we saw there were 10, and we did it by math. Now this is the way I like to think of it. I do it just like a permutation, and then I divide by the smaller number factorial. There is a formula, that's more of a procedure. There is a formula, and it looks like this. N factorial, n minus r factorial, and then an additional r factorial. Would you have guessed that one ahead of time, or did you, Joel? All right, let's look at one more example of that. And, oh yeah, I wanted to do that same one with the formula just to see if it came out to be 10. All right, so I put in the 5 minus 3, and then that additional 3 factorial. I saw 5 minus 3 is 2 factorial. Rewrote the 5 factorial and canceling the 3 factorials. Reducing by a factor of 2 with the 4 and the 2, and I got 5 times 2 is 10. All right, so you have some choices to make. All right, let's do one more example of that besides a committee of people. Here's what's going to happen now. You're going to look at problems, and you have to decide whether you think order matters or it doesn't. So is this a combination or is it a permutation? The situation is I have a 5-card hand dealt to me from 52 cards. How many possible different hands could there be? So this is a practical problem. If you're going to bet your life on some sort of a card game, you need to know the odds. So how many possible different hands are there from 5 cards from 52 in a normal deck? So first of all, is it a combination or a permutation? If you had the ace of diamonds, 2 of diamonds, 3 of diamonds, 4 of diamonds, and say you had those 5 cards, ace, 2, 3, 4. Ace, 2, 3, 4, I'm sorry, and 5 of diamonds, so that'd be 5 cards. Would that matter? Would it be a different hand altogether if you had ace of diamonds, 3 of diamonds, 2 of diamonds, 4 of diamonds, 5 of diamonds? No. The order doesn't matter, so that means we are in a combination, just like on a committee, and we're going to have 52, a combination of 52 objects taking 5 at a time. And when this is my way, I like to draw my 5 blanks. I do it just as if it was a permutation, and then I reduce it by that factor of 5 factorial. So that's what I do. So I put in, there's 52 ways to fill in the first card spot, and then 51, and so on. And using the formula, I would do this. And either way, it comes out to 2,598,960 different hands 5 card hands. Alright, well you can chew on that for a while and hope you have a good night, and we will be back together tomorrow to exercise some of these principles. So have a good one. Oh yeah, Morgan won't be with us tomorrow, and I promised to show her the numbers that we'll be working on in our books. So we get that for you. And everyone else, you can ignore this part, but that's our goal. And I can send you a text tomorrow, not a text, you know what I mean, an email tomorrow on your school account to tell you about how far we got on that. I'm anticipating we'll finish that. So, all right, see you in the morning. Good night.